All right, so in this particular center of mass problem, you have a rod that has a mass per unit length of 390 grams per meter, and it said it's bent into a Z shape. So the diagram is shown below here. Here's segment A, segment B, and segment C. The length of each of the segment is given, and that's it. And it wants to find the center of mass using IJK unit vector notation. So let's go and crack this out. Okay. So to do center of mass, I'm just going to apply the function for center of mass, and that is XCM is equal to the mass of each segment relative to where the center of mass is in that direction for each segment. All right. So XCM here is MA XA plus MB XB plus MC XC. I have three terms here because the particular rod is broken into three segments, and then on the bottom, rather than writing M1 plus M2 plus M3 or MA plus MB plus MC, I'm just going to write M total. Okay. Now, so to do this, we need the mass of each of the segments. So the problem didn't explicitly give us the mass of each segment. It gives the density, which is 390 grams per length. All right, so let's go ahead and find mass. To find mass is pretty light work. All you have to do is take the length given, times it by the density, the linear density here of each segment. So 1.1 meter is for length A, and that is 390 grams per meter. So if you do this correctly, the units meter here will cancel out. So therefore 1.1 times 390 is 429 grams. I'm just gonna leave it in grams here. I'm not gonna convert it into kilograms because the unit for mass, as you can see, there's M on the top and then there's M on the bottom. So the unit will naturally cancel out, so the ratio stays the same, okay? Here, I'm also going to do MB and MC. For this particular problem, I'm just going to make the statement that says MB is equal to MC because if you read the problem, it says segment B is 0.45 meters, but segment C is also the same length. So same length, same linear density, therefore same mass, okay? So MB is equal to MC, which is equal to 0.45 meters times the linear density here, which is 390 grams per meter. And meters again will cancel out, and then that'll give us the mass of each segment B and C as 175.5 grams. All right. So now all we have to do is really just plug and chug. But I think the tricky part is identifying XA, XB, and XC. So if you keep up with this particular one, it won't be too bad. So for each segment, I like to identify the center of each segment. So here are the little dots. So if you look at segment A, there's the center for that segment. If you look at segment B, here is the center for that particular segment, and likewise with segment C, okay? I like to do just because I think it helps prevent you from goofing off on how to measure the length relative to each segment. All right, so well, I already know what MA is, I know what MB is, I know what MC is, but now I need to figure out XA, XB, and XC. So if you keep up with this here's how you should measure XA, XB, and XC, and that's just measure the length away from the vertical axis here. The problem tells us that length A is 1.1. But you notice here the center of it would just be half of that, right? So it'd be 1.1 divided by 2. And then here, where B is, there's the dot. If you measure the horizontal distance to this location here, that would be the length of A, which is 1.1. And then last but not least, if you do it for C, well, we already know that length A is 1.1, but then this also occupies half of length C. But length C is 0.45. So if you do 0.45 divided by 2 and then add that to 1.1, that'll be your XC, okay? So here in my work, the mass for A here, I already calculated, which is 429 grams. Here is 0.55 because my blue arrow is only half of 1.1, which is 0.55. And then likewise, MB I already found using the linear density there. And then, well, how far is it from the vertical axis? Well, it's 1.1 meters away because that's the length of A. And then last but not least here in this particular segment, that is the XC value. XC, once again, is 1.1 plus half of 0.45. So if you do that correctly on your calculator, you get a value of 1.325 meters, okay? And then we just divide by the total mass of the whole entire system, and that will give you an XCM of about 0.848 meters. And then we can do the same for Y. So really the function is exactly the same, except now you just have to figure out what YA, YB, and YC is. So if you watch my work here, I'm just gonna reference these little center dots that I've drawn for you. So I'm just gonna go ahead and cancel out MC and YC because if you look at segment C lies on the horizontal axis, which means it didn't, well, there's just no Y value, right? So it lies, because it lies on the x-axis, there's no y value. So I'm just going to cross that out because mass times 0 is just 0. Now, we need MA, YA, MB, and YB. Well, MA and MB we already know, so let's find YA. So if you can just draw the vertical distance from the horizontal axis up to where that dot is, well, this segment here that I've drawn for you, that is just the same as length B, but length B in the problem is given as 0.45. And then I'm going to draw this length here, okay? This length here is also half of B, so 0.45 divided by 2. So if you do this correctly, MA I just carry down, YA is 0.45 because again it's the entire length B which is given, and then for this second dot here, from the horizontal axis up to that dot is only half of length B, and half of length B is just 0.225. Divide that by the total mass, and then there you go. You get 0.298 meters, and then if you want to express this in IJ unit vector, it would just be 0.848 I plus 0.29J, and everything is positive in this particular diagram, so everything needs to be positive here in your unit vector notation, and that's that. Okay, all right, I hope that helps. Stay nerdy, don't be wired.